Good afternoon, grade 12 mindsetters, and welcome to it. It's Mindset Learn Extra, and I'm Katleho. I'm going to be with you for an entire hour, and I'm not alone in the studio as usual, you know. I'm with this brilliant genie of a teacher who will make sure that they'll be breaking all of those particles and everything that we'll be learning physical science-wise for you at home. Hello.
Hello. Kadleho doesn't know my name, can you tell? I'm Tracy, by the way. It's all right. We're new. We've just been introduced, so it's okay. Don't worry. It was quite brief. Hello, guys. Well, just remind you today what we're going to be doing is we're doing applications of redox. So last week you did galvanic, electrochemical cells. Today we're going to look at some of the applications. So hang in there. It's actually a really nice section. I like it. Yes.
Awesome, 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 awesome. Grade 12s, remember that you get in touch with us on Facebook. We are www.facebook.com/learnextra. We are on Twitter at learnextra, and make sure that, of course, the notes are there and the scheduled and everything. And we're going to be posting a challenge question as well that will be else surrounded with what we're learning today. And for you at home, just make sure that you get in touch and interact and perform as much as you can, and you'll stand a chance to win this beautiful Casio calculator, proudly sponsored by Casio. And I'm going to be doing another round of that beautiful Vodacom hashtag Get Connected competition challenge, where we'll be giving away 55 rands worth of airtime. So just make sure that you don't go anywhere, you don't touch that dial. And grade 12, I'm going to be giving you information as well on the beautiful learners competition that we've got just starting on the 15th of September. But right now, I'm just going to throw it away to my teacher. Take it away.
Thank you. And then I get to butcher some people's names when we take them out the draw. It's fun. It was fun last time. Anyway, okay, guys. So what we're doing, I've changed the board again, is we're looking at redox reactions, and really we're looking at the applications of redox reactions. And these are quite important. I think you are going to get at least one, okay, because they're industrial processes and they're actually quite important to us as a country. So what we're actually looking at today is we're going to look at the applications of redox reactions. Okay, so we need to obviously have our challenge question. So here it is, and our challenge question says, the net or overall cell reaction taking place in a certain cell is represented as follows. So we have water as a liquid plus electrical energy gives me hydrogen plus oxygen. Which one of the following statements best describes this cell? So the cell is an electrolytic cell in which an exothermic reaction takes place. B, an electrolytic cell in which an endothermic reaction occurs. C, a galvanic cell in which an exothermic reaction occurs. Or D, a galvanic cell in which an endothermic reaction occurs. All right, so I want to know this cell with the water plus electrical energy goes to hydrogen and oxygen. Is it an electrolytic cell that's exothermic, an electrolytic cell that's endothermic, a galvanic cell that's exothermic, or a galvanic cell that is endothermic? Now, I don't just want a guess, okay? So if you're going to put in A or B or C or D, whatever your answer is when you try answer on the Facebook, okay, guys, I need a little bit of an explanation. Now, only one of these are correct, and I sort of need to know where you came up with the answer. And why I want you to do that is I need you to get used to the fact that with your multiple choice in your exams, sometimes I know we have to guess, but you really should be thinking through them and working through them. You have plenty of time in your exams, okay? So don't just guess. All right. So remember, you can get them on the notes that you can download. So let's jump straight in. All right. First thing is my very not so focused picture, but that's okay. We're going to look at the refining of copper. And this is quite important because obviously we're a mining country, but this is such an interesting system that works this out, okay? What we have over here is our energy source, okay? Now, this energy source over here, my positive side is over here, my negative is over there. I don't actually care whether it's from a cell, though for refining of copper, we're probably going to have it connected to the grid, okay, and then have it changed into a DC current. Over here, what this little strangely shaped thing is that is what we call a copper ingot, okay? When we mine copper, we get the ore, we start to refine it, and then we get copper bars, okay, or copper ingots. These aren't often 100% pure. Inside of this, we have metals like platinum, gold, silver, and that was silver and then gold. And we can't use this copper as it is because it's not pure. We want pure copper, and this is also one of the reasons why copper is so expensive, okay? So this is my impure ingot, okay? It is connected to the positive side of the cell, so this is actually my positive electrode, okay? On the other side over here, we have a very, 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 very thin plate or rod of pure copper. So we need a little bit of copper to start off with, okay? Inside the solution, so this solution over here is our electrolyte, and it would be something like copper sulfate, for example, okay? Now, we need that because I want copper 2+ ions. Okay, now this is what happens in this situation, okay? Is we need, and I think I've actually got these the wrong way around. Watch that. No, I don't. Nope, I was just checking. Okay, remember, at the anode, whether it's a galvanic or an electrolytic cell, at the anode oxidation takes place. So at this point, at this special anode over here, so this is my anode, it's the positive one, the copper that's in this ingot changes to become copper 2+ plus 2 electrons, okay? And I think I've got this the wrong way around. No, just let me check. No, I'm right, it is positive. Sorry, I have my moments, it's been a very long day. Anyway, so copper goes to copper 2+ plus 2 electrons. Those electrons come up and they go towards the positive part of the cell, go through the cell, come through, go to the cathode, okay? So this is the anode over here because that's where oxidation takes place, always, without exception. Here's my cathode, okay? Now, at the cathode, what happens over here is these copper 2+ ions, so now we just create more copper 2+ ions into my solution. They come over here and they go, oh, yay! I can see the electrons. Yes, we get very excited. And over here, the copper 2+ ions go, thank you very much. I will take those electrons, and they form copper. And what happens is this becomes plated in copper metal, okay? Pure copper metal. Over here, down the bottom, okay, this becomes a sludge or a slime, and that's got things like the silver, the gold, platinum in it, and then they can take that out. And this is a batch process, so they put a set of anodes and cathodes in, they do the reaction, the anode disappears, get a nice big thick cathode, they take that out, they do it again, okay? So basically what happens is we are oxidizing copper to reduce copper 2+ ions to become copper metal, okay? So basically we're forcing the copper from the anode to the cathode by taking and giving away electrons, okay? Nice, easy reaction. So, now, extraction of aluminum. I actually love this process because it's a really nice one, but listen carefully to what I'm saying to you. First of all, we extract aluminium from bauxite. Bauxite is aluminium oxide, which looks like this. Now, what actually happens here, guys, we don't have a lot of aluminium resources in South Africa, despite our many other mineral resources and our extreme wealth, which is so nice. But we have some, but not enough. We do have an aluminium smelter in Richards Bay, which brings in a lot of foreign exchange. Because what happens is, aluminium gets mined in Australia, okay? And it comes out the ground in Australia as bauxite. They put it on a ship, and they ship it to Richards Bay. Okay, they obviously do some of it in Australia, but then they ship it to Richards Bay. We then take that bauxite, through the process I'm going to describe to you now, we refine it, we get this aluminium metal, and then we ship it back to Australia. This to me makes no sense, this is why I teach science and not business. And we ship it back to Australia, they make aluminium products and stuff, and guess what? We just ship it back and buy it back from them. Anyway, moving on. So goes life. That's the whole way business works. I have no clue how that works, but I do know how this works. Okay, so we get this bauxite, and we're going to do this through an electrolytic process. Now, we could take this aluminium oxide, just melt it, smelt it, okay, and off we can go. But if I melt the aluminium oxide directly, it melts at about 2045 degrees Celsius. That is extremely high. Very expensive, lots of electricity, becomes very, very dangerous. So instead of that, we have to take that aluminium and we dissolve it in a solution known as cryolite, okay? And this cryolite, I've just got to get its formula, which I've got somewhere in my notes, because I can never remember the actual, so it's this. So this is known as cryolite. Now, the reason why, and I think it's IT, the reason why we need the cryolite grade 12s is because it takes this melting point down to 950 degrees Celsius. That is huge, okay? Reduces costs, okay? And in a country such as ours, where we know our electricity is precious, this is big for us, okay? Because the smelters use a huge amount of our national grid, which is fine because we are used to the one in Richards Bay, okay? So we take the aluminium oxide, dissolve it in cryolite, which we can then make into a molten solution, okay? Brilliant. Then what we do is we take that solution, okay, and we put it into our cell. Now, what makes this cell very special is over here, these blocks over here. This is my anode, okay? So these here are my anodes. All three of those are my anodes, okay? And they're carbon anodes. And they're my positives, okay? This, the lining of my cell, that part, is my cathode. It's also carbon, okay? But it's the lining. So it's also carbon. It's the lining of the cell, which is different. Up to now, they've all been right. There's a reason why we need to do this. Inside this solution over here, okay, what happens is the aluminium in the oxide gets reduced, okay? So my aluminium goes from being aluminium 3+, it takes 3 electrons, and it becomes aluminium metal. And actually, it becomes a liquid over here because it is denser than the cryolite. It's at 950 degrees, so it's liquid still, and they can pour the aluminium out, okay? At the anode, which is where my oxidation takes place, my oxygen, which was O2 minus, gives away its electron and becomes oxygen gas. Sounds pretty straightforward. However, one of the issues with our aluminium smelter is that the carbon rods have to be replaced often because this O2 is being created at 950 degrees Celsius. That is extremely hot. That results in the oxygen reacting with the carbon electrode, and as a result, from those carbon electrodes, carbon dioxide gas comes off. Environmental issue, okay? So it's one of the issues that come off. The fact is that we are creating carbon dioxide gas, greenhouse gas. Bad idea. Uses a lot of electricity. So those are big considerations. Also, because these carbon rods get used up so much, we have to replace them often. And it sounds, oh, it's just carbon. We mine it. It's not as easy as that because it's not like charcoal or the lead in your pencil. It's got to be produced, and they're expensive. Okay, so we've got to be careful. So with your aluminium smelter, what's important is the aluminium gets oxidized, the oxygen gets, so aluminium is reduced, oxygen gets oxidized, okay? The cell lining is your cathode, and then we have our carbon anodes. Very important thing to remember here, whenever we look at like the electrorefining of copper, the extraction of bauxite, the aluminium, the metal without a charge always gets made at the cathode because the metal takes the electrons. The metal has to be reduced, okay? Now, it's a great process. It's not a difficult process. It's a nice, easy one to understand, but just be careful with the anode. Remember, if they ask you about what reaction happens at the anode, they want the one with the oxygen. Then they'll say to you, what happens, why do the carbon rods have to be replaced, or what are the environmental issues? And that all comes down to the fact that it's happening at 950 degrees Celsius. The oxygen reacts with the carbon rods and becomes carbon dioxide. Okay? Now, today, I'm sure you realize we've got lots of theory to get through. I have one more thing that I want to do with you, but I think what we're going to do before we hit the production of chlorine, which is great, I love it, we're going to take a quick break, I think, Kakleho?
Of course.
I said that so bad. I am so sorry. I'm going to be butchering lots of names today. But they all understand. They all laugh at me. Anyway, and then we will jump into some questions after we've done that.
Awesome.
Okay.
Remember, mindset is to go to our Facebook page, and then you go to the notes, test yourself, and then answer as many questions as you can. And you can stand a chance to win this beautiful Casio calculator. And at the end of the show, I'll be announcing a name of our grade 12 winner from last week. So during the break, go there to our portal, answer as many as you can, and next week, I might be announcing you will be back after this breather. Welcome back, Mindsetters. You're still tuned to Mindset Learn Extra. I am Katleho, and I'm not alone in the studio. I'm with this exciting teacher of mine who just keeps pumping energy on me throughout the ad breaks. But I hope you went to our Facebook portal and you liked and you did the drill as I asked you. And of course, I'm introducing a beautiful, beautiful competition where it's like #GetConnected, where you stand a chance to win beautiful, beautiful airtime prizes sponsored by Vodacom. And I'll be announcing 3 names of the winners for today. So just make sure that you keep tuned. But right now, I'm just going to throw it back to our teacher.
Oh, thank you. Since I got new, fresh meat for telling my stories too. Anyway, moving on. And by the way, if any of my grade 11s are watching, I know they shouldn't be because they're in grade 11. I was talking about your ears were burning. Anyway, moving on. So, okay. Now we're going to do the production of chlorine. I love this. Now what they've done, and I actually quite like this, is this used to have 3 cells. There used to be 3 ways to produce chlorine, but we've only using the 1 cell. And it's known as the membrane cell, okay, which is exactly what it says it is. And the reason for that is the other 2 cells, one was called the diaphragm cell, the other one's the mercury cell. Huge, huge environmental issues with them, okay? So the diaphragm cell had asbestos in, and the mercury cell had mercury in. Obvious environmental issues. And in fact, in Europe, since 2012, it's been illegal to have either of those cells operating. They have to have one like this, okay? Now, it's such a nice cell, but you've got to be careful here, grade 11s. Grade 12s, I apologize. I do that to my kids all the time, but you are grade 12s. Be careful, be careful, be careful with the reactions, because it's not quite as simple as it seems. Essentially what happens is they take brine, seawater, salt water, okay, NaCl, and they pump it into the anode. Okay, remember the anode? Positive electrode. At that anode, what happens is chlorine, remember NaCl is made up of Na plus ions and Cl minus ions. So at the anode, the chloride ions lose their electrons, become chlorine gas. Nice and easy, that's the first part, because we're making chlorine. So out over here comes Cl2, the chlorine gives away 2 electrons, everyone's happy. But what actually happens is between the anode and the cathode is a membrane. It is a semi-permeable membrane. Okay, it's actually an organic polymer. What makes this so special is actually only cations, positive ions, can pass through it. So what happens is the Na plus ions pass through the membrane into the cathode. Okay, but here things aren't as simple as we would expect, because normally we would go, well, if the Na plus is going to the cathode, what we've done for the last ones is the metal goes to the cathode and we end up with Na metal. However, that is not what happens. Because water has a better oxidizing agent who has a higher reduction potential. The water, because they're actually pumping in water at the top here, water gets reduced. Not the sodium, not the Na plus, okay? So at this anode, which is your cathode, sorry, which is your negative, water is being reduced. Now, I'm not sure you can actually see it properly, but the water is going H2O, takes the 2 electrons, and here it now forms hydrogen gas and OH minus ions, okay? So now hydrogen gas is coming, ooh, that's terrible. Hydrogen gas is coming off the top. So now I've produced chlorine gas and I've produced hydrogen gas. This is what makes this whole industry so amazing, is because I've got Na plus ions, and over here I have OH minus ions. So the NH plus goes, oh, look, negative, I like negative, plus positive, negative is negative, positive, opposites attract, yay! What do they form? NaOH, sodium hydroxide, caustic soda. So this process is amazing because I get no waste products. I get chlorine gas, hydrogen gas, and caustic soda, sodium hydroxide, all of which have hundreds of uses. Remember, chlorine is used in bleaches, disinfectants, used for making hydrochloric acid. Hydrogen is used in the Haber process, used to make ammonia, used to make fertilizers we carry it on, hydrochloric acid, moving on. NaOH used to make soaps, it's caustic soda, it's an incredibly important industrial base. So it has lots and lots of uses. That makes this process so economical in a lot of ways because we don't get a lot of waste, so we don't have a lot of stuff to throw away. And because we're now using this organic semi-permeable polymer as your membrane, it's great because we don't have to worry about the environmental issues, though there are environmental issues because this is an electrolytic cell. So this cell requires that I add in a current, okay? But now be careful when it comes to your overall cell reaction. I just want to take this off over here because if we look at our reactions, okay, the point here is that the cathode has nothing to do with the sodium, the anode has nothing to do with the sodium, but when I put the overall cell reaction in, I've got to include the sodium. The sodium, to a certain extent, is a little bit of a spectator ion, but it's not really because I don't get the same products, well, obviously if I'm not using sodium, but if I used potassium chloride, I wouldn't get the same thing with the potassium hydroxide, okay? So this is a very specific reaction to produce chlorine, hydrogen, and sodium hydroxide, okay? I love this reaction. All right, so, brilliant. Let's jump into some questions, okay? So we've got a quick one here. A strip of aluminium is placed in a beaker, brilliant, containing a blue solution of copper 2 salt. After a while, the solution becomes colorless. Guys, this is really important. The blue solution comes from the fact that we have Cu2 plus ions. If the Cu2 plus ions disappear, that means I'm going to be forming copper metal. The Cu2 plus ions are being taken out of the solution, okay? Then they ask, how would the reading change as the reaction proceeds? Well, the solution changed color all by itself. Because it changed color all by itself, that means it is a spontaneous reaction. So I could essentially, if I set it up right, make a cell out of it. That means it's a spontaneous reaction, which means it would be a galvanic cell, which makes it means that it's going to increase, okay? My reading would increase. So it's going to increase. Why? Because it is a spontaneous exothermic reaction. Okay, it will be a spontaneous exothermic reaction because I didn't need to help it. It would happen all by itself. Then, refer to the reducing ability of aluminium to explain why the solution becomes colorless. If we look at our redox table, okay, and remember we use 4B. If you've been taught to use 4A, that's fine. Just go with me with what we're doing. So we started with copper 2 plus. Let's have a look at it. So copper 2 plus is over here. Okay, and we started with aluminium, so let's find the aluminium. The aluminium is over here. Okay, so what is happening is that aluminium, okay, if you look at it, the aluminium minus 166, but it's higher on the redox table, okay? As we go up the redox table, this increases, listen to me, their reducing ability, okay? In other words, the higher up on the table for 4B that it is, the better reducing agent it is. Think that just didn't make any sense whatsoever. Okay, it's a better reducing agent when it's higher up on the table. Okay, so in other words, that it will force the copper 2 plus to be reduced. Okay, because it has a higher potential. It will force it to be reduced because the aluminium is a better reducing agent. Okay, so that leaves us with the next one. Now write down the balanced net ionic equation. Ionic, that's great. That means we can leave in all the charges for the reaction that takes place. So let's go back over here and we start, well, we're going to start with the aluminium. It's the better reducing agent, which means the aluminium is going to get oxidized. And now, just as a little trick, and this is something I do, okay, you might have been taught something different. It's all right. I want to show you something. It's a little trick. And but this only works on 4B, okay? And this is what I tell my learners to do, because it always helps, because often the problem is, I don't know which way to write them. I know, so listen, okay? And yes, I need more sleep. We all understand this, okay? But I always do. Okay, so we're starting with aluminium metal and copper 2+ ions. Unless it is very clearly stated to you, grade 12s, that you have copper 2+ going to copper ions, or copper 1+, because there's another copper equation further down over here, don't use those two, okay? So unless they make it very, very clear in the instructions that you're using copper 1+, ignore those equations completely. You're going to use the copper 2+. So I've ringed the aluminium and the copper 2+, because those are my reactants. That's what I started with inside the container, okay? Now what that means is my aluminium must be written this way around, my copper must be written this way around, and if I join them together, it makes a Z. Some of you might have been taught to C. Everyone does this differently, okay? The fact that it makes this nice Z also tells me that it's spontaneous. So it helps me. It makes me know that this would actually make a galvanic cell, okay? But the aluminium, I need to write from right to left. So it becomes aluminium, becomes aluminium 3+. I'm not sure I could write it any bigger if I tried, but hey, there we go. And the copper is copper 2+ plus 2 electrons. So it's copper 2+ plus 2 electrons, and that goes to copper. But now the question was, write down the balanced net ionic reaction. This is not the net ionic, and it's not balanced, because balanced means that if I add these two together, I sort out all the electrons. So we look at this and we go, well, there's 3 electrons there and there's 2 electrons there. Guys, I have to do something here, because if I just add these together as they are, I'm going to have an electron left over. And electrons can't exist on their own. They can't just run around in the solution and we have this random electron doing whatever it likes, okay? It can't happen. There has to be the same number. So however many electrons the aluminium gives away, the copper needs to take all of them. And we go, this is a 3 and that's a 2, so that means we need to find a common multiple, and that's going to be 6. So I'm going to take my aluminium oxidation reaction and I'm going to times it by 2. And I times everything in that reaction by 2. So that gives me 2Al, which then gives me 2Al3 plus 6 electrons. Okay. I'm going to times the copper by 3, because now I get 3Cu2 plus 6 electrons, which then gives me 3Cu. And why we're doing this is because now we pretend like we've got a maths problem, because over here, and I'm having fun with all the colors today, I don't know if you noticed, the electrons disappear because we've got 6 electrons on both sides. So that gives me 2Al plus 3Cu2+, which then goes to 2Al3 plus 3Cu. This is a balanced net ionic reaction, and it's balanced in 2 ways. 1, we have the same number of each atom on both sides, and 2, the charge on both sides is the same. 3 times 2, that means this has got an overall 6 plus charge. 2 times 3 overall charge of plus 6. So that's the same. Also, if say they'd asked you to put in the spectator ions, which they didn't, but they could have, okay, if I put the spectator ions incorrectly, my overall net reaction will be balanced as well. It's actually a cheat to balancing difficult equations if you can reduce it down to the oxidation and reduction reaction. Okay, now from here, because I know this was my that's not going to help. That's the oxidation. That's the redox. Okay, so I could work out the cell potential if I wanted to, because remember, you go cathode minus anode, reduction half reaction minus oxidation half reaction. It's written in 3 ways. You can use any of them. Okay, so this makes it nice and easy. Ionic, leave it as it stands. Okay, if you had got one of the reactions where they have phases, all right, so if we look over here, we got a little bit further down. So over here, for example, if you were dealing with mercury and you needed to write this equation down, guys, if you write an equation down from the redox table and it has a phase in it, like liquid, gas, any of those, you must put the phase in. Okay, don't leave it out. Secondly, I needed you to note that's got a double arrow. These are reversible. Watch, when I wrote them over here, arrows in one direction. Okay, my kids have a good giggle when I say that every single time. They go one way. You must make a choice. Okay, and we don't, out of principle, write them going backwards. So we don't write an equation where the arrow goes to the left. We just don't. We read from left to right, so the arrow must go from left to right. Be careful there. Okay, I think, guys, because the next question's a little longer, that is actually a good, I know it's a little early, but it's a good place to take a bit of a break, and then we will do the challenge question when we come back and do one more question. Yeah.
Of course, thank you very much for that. Of course, we're going to go for a quick break, and we'll be back and we'll be answering all of your questions. And I'll be announcing the winners of the draw for the Airtime #GetConnected competition after this. And of course, before the end of the show, I'll be announcing the winner of the Casio calculator. So just make sure that you don't touch that dial, you don't go anywhere, and you come back and study more with me and Tracy.
Yeah, to think about that.
Welcome back, Grade 12 Mindsetters. I come bearing gifts as usual. So I'm here to be doing the draw with Tracy here and making sure that, of course.
He's taking advantage of the fact that he's taller than me. I want Looney back.
Making sure that, of course, we give you airtime that you deserve. So do the honors.
Okay. Okay, you do. They realized this from 2 weeks ago, Looney. I just butcher all the names completely. So, hey, what the heck? Okay.
Let me help you.
There you go.
The first airtime goes to Michael Ramfumezi.
Okay, we gave it to him.
Michael Ramfumezi. So you walk away with airtime sponsored by Vodacom, worth of 55 francs, coming your way. Moving right along.
They need to give me airtime. I'm a teacher. You know.
I have here Mkati Olile.
Like I was going to say that. Hello.
Mkati Olile. You also working away with airtime voucher worth of 55 francs from Vodacom.
Last one?
The last one is...
There we go.
Should I attempt to make you call it?
There we go. Lindo Koza.
Yeah, Lindo Koza.
Lindo.
We're also working, Lindo Koza. We're also working away with airtime voucher worth of 55 francs, sponsored by Vodacom. So that's where it stands. Thank you very much for that.
Sorry, we're only shaking our head because our director's confused. So it's cool. Okay.
Thank you.
So, thank you. So you guys have money, yay, for your phone, which is even better. So, okay. So, guys, let's go back to the challenge question before I do the last one. And I know Katlego said there are definitely people who have got some answers, which is great. I love it when you interact. And, of course, the question was whether the H2O, what type of cell it was. And it was A, B, C, or D. And basically, it was whether it's electrolytic, galvanic, and then exothermic or endothermic. So, hit me with some of the answers. What sort of things were they telling me?
We have Levi or Levi Tahudi Tokwane saying it is B because it needs startup heat, and heat is needed to start reaction, which is endothermic.
Okay. Good.
And then we have one here. Okay, let me just get... Okay, the other one is a question. It's saying, what is aluminium extraction?
Oh, well, that's what we just did. Guys, aluminium extraction is just the purification of aluminium. It's just how we refine it once we take it out the ground. Yeah.
Alrighty. We have one here also from Dimpo Molepo who's saying B, because electrolytic cells are non-spontaneous. The addition of electrical energy indicates that the reaction is not spontaneous and requires energy to occur.
Oh, we have such clever grade 12s.
So, and then one, Emmanuel says B, because electrical energy is added to the reactant R.
Oh, you guys are amazing. I actually think you guys got it. So it actually wasn't much of a challenge question. Absolutely 100%, guys. It is B, because the hint here was the fact that we said electrical energy as a reactant. Okay, as soon as I have to add in electrical energy, it makes the options an electrolytic cell. And electrolytic cells are definitely non-spontaneous, and they are endothermic. Okay, because they need lots of energy. So it's definitely B. I don't think you guys need me. I think we need to shut the show down. It's time to go home. Okay. No, I'm only kidding. I want to get paid. No, we still got some more. And I'm having fun with colors today. So let's go to the next question. All right. So, next question. And hopefully this helps with the whole aluminium thing as well, sweetie, who's asking that. Now, aluminium is one of the most abundant metals on Earth. Yet it is expensive, largely because the amount of electricity needed to extract it. Aluminium, always called bauxite. Bauxite is purified to yield a white powder called aluminium oxide, from which aluminium can be extracted, in other words, removed. The diagram below shows the electrolytic cell for the extraction of aluminium at temperatures as high as 1,000 degrees Celsius. Okay, and this is in an iron container. We've got our carbon electrodes, there's a drain, molten aluminium. Now they say, number one, state the energy conversion that takes place in this electrolytic cell. Now, whether you understand the aluminium process or not, it doesn't matter. The point here is that electrolytic cell always goes electrical energy, okay, to chemical. There is absolutely no exception to that, okay? It's always electrical to chemical. Is aluminium formed at the positive or negative electrode? So, what we just did is, the carbon electrode is your positive. That means the negative electrode is the container. The aluminium comes in through the drain. That means the aluminium is being made at the negative electrode. It's been made at the cathode. So here, it's negative. Okay. Use the table of standard reduction potentials to write down the half reaction for the formation of aluminium. So we go back to our table. We're dealing with aluminium, which is actually what we had over here. Now, in the last question, aluminium was our reducing agent, but this time I'm making aluminium. So this doesn't help me, because what we're actually going to do is we're going to make aluminium. So this time I'm going to go Al3+. So it's over here. Al3+. Plus 3 electrons gives me aluminium. Okay, we're doing well. Also, the fact that we've got Al3+ also reminds me that then the aluminium goes to the negative electrode, because it's aluminium 3+. It's positive. It's going to be attracted to the negative electrode. Okay? Then explain why carbon dioxide is formed at one of the electrodes. This is just what I was telling you before the break. Oxygen is formed at the anode. Okay? So oxygen gets formed at the anode. The oxygen reacts with the carbon and forms carbon dioxide gas. Okay? And because of the high temperature, that's going to happen all by itself. We do not need any help. Okay? So the oxygen reacts with the carbon because of the high temperatures. So now the question becomes, why should the carbon electrodes be replaced? Well, if the carbon is reacting with the oxygen to form carbon dioxide, it means that those carbon electrodes are actually being eaten away. They are disappearing. So eventually, we have no carbon electrode left for the reaction to happen. Okay. Then, write down the 2 negative effects that the extraction of aluminium can have on the environment. Well, there's actually a couple, but the biggest one is pollution. Okay, this is one of them. And that pollution comes from things like CO2 gas is formed, so it's a greenhouse gas. There's pollution from the production of the electricity needed, especially if it comes from coal. Okay. And the waste, there's a lot of waste. Okay, so the waste product is actually this horrific red mud. Okay, so it's a waste product of mud which has aluminium and all sorts of funny things in it, and whatever was in the bauxite to start off with, that aluminium oxide before it came to us, and that red mud ends up in our groundwater and in streams and lakes and stuff and dams, and it becomes a bit of an issue. Okay, some people, and this of course is, this is one of those things that can be quite controversial. There can be also noise pollution, though I'm not sure that would be completely defined as an environmental issue. Okay, and wow, we got through that one really quickly. That means we can do the last one. Yay! Okay, last question. No, that's not it. That's it. Yay. So, industrially, chlorine is produced by the electrolysis of brine. Brine means sodium chloride solution. Okay, in addition to chlorine gas, hydrogen gas, and sodium hydroxide is produced. Yay. Write down the equation for the reaction that takes place at the cathode. Guys, this is learn work. All right, this isn't something that I expect you to be able to always work out. This is something you need to learn. Now, it's an electrolytic cell, okay, which means the anode is positive, okay, the cathode is negative, and we learn that hydrogen gets made at the cathode. So now if you can't remember the reaction, we go back here and we say, okay, fine, I'm putting in water into the cathode, okay, I'm putting water in and I'm getting hydrogen out. Now you can go all the way down your table and look for all the reactions with water and hydrogen. That's the one we're going to use. It's the only one we're going to use. And we learn that we need the OH minus. So I look at this and I go, well, it's 2H2O. So I'm going to put this in over here. So it's 2H2O plus 2 electrons, which then gave me H2 gas. Let's just quickly make sure I've got it right. H2 gas. Let's put it in the right phase. Plus 2OH minus. Okay, so we're quite happy. Oh dear. Now, write the balanced overall reaction, omitting spectator ions. Okay, now we've got to be careful because the one I gave you earlier included the spectator ion of the sodium. So now we're going, okay, now we're going to go, do they want the sodium? Do they not want the sodium? So now we think about it and we go, well, we know the chlorine's getting made, and hopefully some of you are thinking with me and go, no, I don't know. And the answer is no sodium, okay? No Na+, guys. The reason why I'm not putting in the Na+ is not because I can see it on my answer sheet, but because a spectator ion is an ion that takes parts of the reaction, but it doesn't change its oxidation number. It's a spectator. So the sodium goes in as Na+ over here, okay? It's Na+ over here, and it's Na+ over here, even though it makes sodium hydroxide. Be careful. Be very, very careful. Now, what we haven't done is we haven't actually put in the chlorine. So the chlorine ion, remember, this is what happens with the chlorine. It goes chlorine, okay, becomes Cl2 plus 2 electrons. The nice thing about this is that the electrons are the same on both sides. So my overall cell reaction is going to be the water, okay, plus the chlorine, which then is going to become hydrogen gas, not Hg. It's not going to turn into mercury. That would just be hysterical, okay? And then I would be worth a fortune if I could make hydrogen turn into mercury. Or not, because mercury is a heavy metal, remember. It's bad for the environment. So we've got Cl2 gas and 2OH minus. Now, what I did with the chlorine wasn't actually needed. It's not what they wanted. All they wanted was that. Okay? And we just check that it's balanced. 4 hydrogens, 2 oxygens, 2 oxygens, 2 chlorines, 2 chlorines. We're all happy. Okay. And I'm going far too fast. Now it says, oh, look at this. Name 2 functions. No, that's the eraser. It's not going to help me. 2 functions of the membrane. Okay, now I didn't actually talk about this. Number one, it allows the cations to move from the anode to the cathode. Okay, number one, allows the anion. And number two, it keeps the products separate. So it allows us to collect the hydrogen gas separate, the chlorine gas separate, and the sodium hydroxide. Makes it very easy to collect the sodium hydroxide because that comes out as a solution. Okay, so we've got sodium hydroxide solution, and we still have salt solution. So if we didn't have this separated, okay, this sodium hydroxide would become very polluted. It wouldn't be a nice pure solution, so we would actually end up with sodium hydroxide and salt coming out, which doesn't really help us because then we got the added expense of having to separate them again, so it's got to go through another process before I can put the sodium chloride back through the system. Okay, so it separates them, allows the migration of the cations, the positive ions, and keeps my products separate. All right, now, use the relative strengths of the oxidizing agents present in brine to explain why sodium metal is not one of the products. So, let's just go back to everything we've been using. So we know we're using the water, okay, so we know we're using this. And we said, let's find the sodium metal. Sodium metal is over here, okay. Now, sodium metal, and we've got chlorine down the bottom here. Chlorine, 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 all the way down the bottom, you see. This is a non-spontaneous reaction, and you go, well, you know what, honestly, why shouldn't we get it? The point here is that the water, okay, is a better oxidizing agent. Okay, remember, as you go down the table, the oxidizing agents become stronger. Okay, so H2O is a much stronger oxidizing agent than sodium. Okay, so the H2O is more likely to make the chlorine get oxidized than the sodium Na plus will. And because this is a better oxidizing agent, it's going to get oxidized rather than the sodium. Okay, I mean, going to get reduced. What am I saying, reduced? Then, oh, look at that. And last question. Wow, I never have this much time left over. So, chlorine is used in many useful products, such as plastics, drugs, disinfectants, all wonderful things. Remember, chlorine can be also asked in terms of your organic, in terms of the making of PVCs, be careful, polymers. Environmentalists are protesting against large-scale production of chlorine. They base their arguments on the negative impact of chlorine, now careful here, on humans. Okay, guys, be very careful. The question is, negative impact on humans. If you start discussing things like the chlorine gas contaminates water, not enough, okay? Even if in your head you're going, well, if the chlorine gas gets into the water supply, then the water supply is bad, the water supply can harm humans. Guys, you've got to state that. There's got to be cause and effect. So, for example, and I wrote a couple of them down because it just makes it easier, all right? So, first of all, chlorine gas is extremely poisonous. If any of you do history, all right, chlorine gas is the basis of mustard gas. It's what they used in World War I, World War II. It is the most horrific death, okay? It is the start of biological warfare. So, chlorine gas is poisonous, okay? Not enough, okay? So, we know it's poisonous, which means because it's poisonous, and I've got it here, it can cause health problems. Guys, we don't expect you, because it's not a biology exam, okay? So I'm not expecting you to be able to tell me that, for example, if you've ever smelt chlorine, I'm pretty sure you know, especially if like you've done it in a pool, it burns your mucous membranes, okay? So it feels like your eyes and your nose and everything is just burning. It's horrible, okay? But as a gas, it's extremely poisonous, so it causes health problems, okay? Now, there's the next thing. Chlorine gas is actually what is known as a nerve gas, which means it can lead to death. Okay? That's a negative impact on a human. Okay? I'm just saying, it's one of those things can lead to death. The next thing, and this is actually from the memo, they said one of the things they put is that chlorine is used in a lot of drug manufacturing, and of course drug overdosing is bad. I think that's pushing it a little bit in terms of negative impacts. I would go this part. If they had said negative impact on the environment, gets into the water supply, just the environment in general, gets into the water supply, damages fish, animals who drink it, plants, makes the water acidic, all of those sort of things, okay? So be careful with the question. Grade 12s, this section is very much a learning section. Make good notes, learn how the cells work, learn how we didn't discuss electroplating, but it's there that you need to learn how the membrane cell works, learn how we extract aluminium, learn where the anode and the cathode is, because then all these questions, if you do enough of them, you realize they're all the same, straightforward learning. Okay, and then next week we're gonna do fertilizers. Yay! I love fertilizers. So that is me. It is now time for me to say goodbye, and I'll see you guys next week. But Katlego needs to say goodbye too.
It's been fun. I just need to announce our winner for the Casio calculator for grade 12 for last week. That is Mama Tuva Ndivo, our grade 12 Casio calculator winner. Grade 12 from last week is Mama Tuva Ndivo. Congratulations. Keep tuned to Mindset TV, and for that awesome K53 competition that's starting on the 15th of September. Just make sure that you stay blessed and you learn. From me to you, it's a goodbye.